Hi everyone, so we are going to work on modeling some systems in Simulink today, and I did a short lab with some of my students on this, but I wanted to just review it real quick so you have it as a reference. So if you go into Matlab and you type in the word Simulink and you press enter, it may take a little while, but eventually you will get this screen that pops up. So this is the Simulink library browser. And this is where you can find all the building blocks. There's lots of different types of blocks here that you can use to make and model various systems. So if you press on this button, it'll bring up a new model window. And this is where you'll actually work with your model. And usually I try to get rid of this thing, so I like to work with just the model here. And what we're going to do is we're going to create a closed loop system. And we've been doing a lot of modeling and transfer functions, so we know that we want to work with transfer functions. So what we can do is go to our Simulink block here and we find continuous. This is where for modeling in linear time space or just linear systems, transfer functions, we'll use these blocks a lot. So we want to have a transfer function, so we're going to bring that into here. And we have a transfer function here. If we double click on it, it will bring up our numerators and denominator coefficients. So let's start with, actually this one is an okay one. Let's start with a simple system for now. And what we want to do is first just do a step function like we did before. Or before we modeled it and just said step a function on a transfer function in the main window, and now we're going to do it in Simulink. So we have a transfer function, we'll go with this one. And now we want to create an input, so we need a step input. So here, sinks are what will capture your signal and sources are what create the signal. So we'll go here, we'll find step, drag it into here, and we can connect it. And usually when you hover over it, the little plus shows up, and that means you can draw a line. We also need to observe what's happening, so you can grab this scope and put it here. One thing that I always do is when I open my scope, so it comes up here, I always get rid of this limitation here. So under history, it says limit data points to the last 5,000. I always get rid of that. It's a default setting, but I always get rid of it. So now we have this plot, and we have a step function. If we double click on it, it's going to go from 0 to 1 at time 1. And this is our simulation time, so we're going to simulate for 10 seconds. So actually, we're going to, well, we'll play this real quick. So let's play this. Okay, and we can see on our little scope here that we have something happening. And actually if we press, this is the best button ever. This is auto scale. So at 1 we have the step happening, and then we see that our function goes to 1 at a certain time. So it's following that step. Okay, great. We might also want to look at the input. So if we double click here and we want to look at 2 axes, so we can change this to 2. And then we have 2 inputs. So we can now look at the top plot will now be the step input, and the output, sorry, the second one will be the output of the transfer function. Okay, so if we, save that, I guess we'll just save it to the desktop. Okay, then we press run again. We can see, there you go. We'll make this a little bigger so we can see it. We'll see our step function, auto scale here, step function here, and then our other one. Let's just for a second make this unstable. So if we make this a -1 here, let's see what happens. So here we're changing our pole, right? So it was a -1 before, now it's a +1. If we press play, oh no, we get something very different, right? So we get our system going off into infinity, meaning it's unstable. So now let's add some feedback. This is a very basic system. Let's add a feedback and a controller. So we're going to rearrange some things here. First, we're just going to do proportional control. And, sorry, I'm working in a smaller window here, so I have to organize all my windows. Okay, so here we are. We're looking at this window, and we want to add, first we're just going to add some feedback. So we need our reference. This is going to become our ref, so I'll call that yref. And this is still our transfer. We'll call this plant transfer function, TF. Okay. So we need an adder. So if we press this button, this will pop up. Our commonly used blocks I use is summer. And we want to compare these two signals, right? Here's the output. If we double click on this, is this right? Yeah, we should be able to name this signal. This will be Y. And here we want to plus the Y ref, but minus the Y value. So we open this up, make this a minus, and now it has our correct symbols. We need one more plant transfer function, or not plant, we need one more function here, and we're going to do proportional control, which means that we're just multiplying it by some value, which is the same as a gain. So we can bring this gain in here, and we'll call this KP for proportional gain. And we'll put it here, and we will see what we get here. Okay, again, we'll look at this signal and the input. And actually, there's another important signal here that we want to look at, and that's actually this. This is the error. And so this is the Y ref minus Y, and this is our important signal. We ultimately would want this to go towards 0, and so we want to look at the error as well. So what we'll do is we'll add one more scope here, so there's 3 axes, and then we'll rearrange these signals. So our first one, make this a little bigger. The first one will be the input, the second one will be the error, the third one will be the output Y. So let's save that and let's run it and see what we get. Okay, so if we double click on this again, auto scale, we see that, well, so our step input goes from 0 to 1, and our error starts near 0 and then actually goes away, so it goes far away from it, and then our output is also going away. So this is actually still unstable, and we'd have to pick a different value in order to stabilize it. So here though we can play around, so actually I'll make an easy problem first. We'll make it stable again, and we'll run this. So here, so now we have a stable plant function, and here this time we have things, our reference goes to 1, and our error here goes to a steady state value, and our output also goes to a steady state value. Although it's not 0, it is stabilizing, and so in this case we should have a bounded input, bounded output stable system. So although we have this is called steady state offset in our error and our output, we still have a input output stable system. Bounded input, bounded output stable system. So that's how we can do our basic this is our basic proportional control, and if we wanted to add in other types of control, we can add in, okay, sometimes you have to play around with these and make them all work out. So say we wanted to add an integral control here, we're going to make this a plus again. Remember when we are doing PI control, we simply add our proportional times the error and add it to the integral of the error times some constant. So we're going to have another constant here. This is going to be now, we're going to do I, so ki, and now we need an integral. So we can go back to our main function, look up continuous, here's an integrator, throw it in there, and move some stuff around. It's important that these are actually readable, so you want to make sure your lines and everything are easy to follow. So here's our integrator, and now we're going to run our system one more time. So now we've implemented a PI control, and I'm not adjusting any of the coefficients here, I'm just using ones for now, and we see our system is indeedly stable. And this time we don't have that steady state error, we're actually going all the way to 0, this is the error, and we're going to our reference 1 on the output. One more thing, let's see if this PI control is any better for the system where we had a pole at at positive 1. So let's save this and run it again and see what happens. We have something that's a little bit better. So we have some oscillation going on here. Let's just check and see if we go for a longer period what happens. So let's go for 100 seconds. Run it again. So here we actually have, it looks like a marginally stable case for the output, but at least we can see very easily how our system is going to react. And now we can play with these coefficients. We can add an I, a D control if we want here, and see how this plant is going to react. So this is a basic tutorial. You can play with it from here, but this is how we set up our basic feedback using our reference or our difference. This is our error signal, and we can look at it using a scope. So play around with this system until you really understand what different types of controls you're adding and the plant functions. So play with MATLAB, it's fun.